All right, so for forces number 2 here, if you have more than one force that's acting on an object, sometimes those forces are not going exactly the same direction, sometimes they're going in multiple different directions. And if you have forces going in multiple different directions, you have to have some method of keeping track of all these forces. The way that we're going to keep track of all these forces is by drawing a picture. It's called a free body diagram. But when you make this free body diagram, you have to be able to tell which forces are going to be important forces to deal with. This is not all forces that might be important in the world, but these are the forces that are important for dealing with these problems. We've got a force of gravity, a force of friction, a normal force, an applied force, and a force of tension. All right, the force of gravity. Which direction does force of gravity always go? Down. It goes down. You can write a little downwards arrow, but we get that it's going down. And if you have a force of gravity, well, how do we know that we're dealing with gravity? If you're on or near the surface of the Earth, we're dealing with gravity. So I'm writing Earth, question mark, but it's are you on or near the surface of the Earth? And you could be all the way up to where the space station is, and you're still close enough to the Earth that you're dealing with gravity. Force of friction. What I'm talking about here is when one thing is rubbing against another surface. So what we want to know is the thing moving versus a surface? And if it's moving versus a surface, there's going to be some sort of friction. And that friction always goes in the opposite direction of motion. I'm going to write opposite to motion. And if we're trying to determine, do we have that? We're just going to say, is it moving versus a surface or along a surface or something like that? Bearing in mind that you could be standing still and still have friction. Here's what I mean by that. If you would be moving were it not for friction, then there's friction there. So if I were to push on some object, like I've got a coffee cup right here, and if I were to push on this object, but just slightly, so it's actually not moving, well, there must be friction, because were it not for friction, it would be moving. Normal force. This is a weird one, because we think of normal as being kind of the opposite of weird, but there's another meaning of the word normal. Normal has something to do with math class stuff. If you have a shape or a graph, you could find...
Excuse the interruption. UMass Boston is in room 15 for those that signed up on Naviance. Thank you.
All right. If you have a circle or a graph, you can find a point on this graph, and we can find that there is a tangent line to this point. There's a line that's tangent to that point. And if you're perpendicular to that coming out, this is called the normal at that point, the normal. The normal is perpendicular to the tangent line. It's just a line that comes straight out of the surface at that point. Over here, it would be directly downwards, normal. Along this line, I would say that's the normal. Over here, that's the normal. The normal is a direction that comes directly out of the surface. Bye-bye. We've got a line that comes directly out of the surface, and that's the normal to that surface. Normal force is perpendicular. I just drew a little like an upside down T. It's two lines that are perpendicular to the surface. How do we know that we're dealing with a normal force? Is the object on a surface? If the object is on a surface, it's going to have a normal force. Frequently we say that it's an object that is on a flat surface and the normal force comes straight up out of it, but that doesn't have to happen. If we have an object on an angled surface like this, the normal force comes straight up out of that surface. If you had, like, here is a beach ball. I'm not going to draw anything else to it, but I put a couple of objects on this surface of this beach ball. Some of them are going to fall off and some of them are going to stay there. Well, that has to do with the normal force is coming straight out for all of them, and the force of gravity is going straight down on all of them, and sometimes that mostly cancels out and sometimes it doesn't. The normal force always just comes straight up out of the surface. Applied force, that's any kind of push or pull, including if you're sitting on top of something. That is a type of push or pull. And it always just goes in whatever the direction the push or pull is. So I'm just writing direction of push/pull. And you just ask, is there anything pushing or pulling? Push, pull, question mark. Is there anything pushing or pulling or sitting on top of this thing? Again, the coffee cup is sitting on the table. In the perspective of the table, there's something pushing down on it. It's the coffee cup. Force of tension. The force of tension is a type, or I'm using it as a type of applied force that occurs, that's going through a rope or a cord or a chain or a string, and it goes in the direction in the direction of the, I'm just going to say rope, in the direction of the rope. And you ask yourself, is there even a rope here? And if there is a rope or a string or a cord and it's attached to the object, then there might be a force of tension going away from the object in the direction of that rope or string or cord. All right, so those are the forces we're going to be looking at, and we're going to be analyzing these different situations here. And on the back of the sheet, we're drawing these out. I'm just going to draw them. How much space do I have? Over to this computer. So I'm going to draw, like, I don't know, 2, and then erase them, and then go on to the next one. All right, so a book sitting on a table. You want to go for simple pictures here. Here's the table. Here's the book. It doesn't need to look like the object. You just need to be able to get a sense of there's an object there. So we'd ask ourselves, is this book on or near the surface of the earth?
Yes.
So we've got a force acting on it. What's that called?
Gravity.
Force of gravity. Which way is it going?
Down.
Down. So we've got force of gravity going down. I like to ask the normal force one next
Yeah,
because
that's what I was gonna say. That
Yeah.
one was.
yeah, I like to ask them in that order: force of gravity, and then the normal force. So I would look at this and say, is it on a surface? It is on a surface. So we've got a force coming straight up out of that surface, and that is actually just straight up, the normal force. And then once we know it's on a surface there, then look at the friction. Be like, is this thing moving, sliding along that surface? It doesn't appear to be moving along the surface, and it's not like, oh, it would be moving were it not for friction, so we're not looking at friction. Is there anything else pushing or pulling on this object? No. If we had another book on top of it, maybe there'd be something pushing, but there's not. Is there any ropes or strings or cords or chains? No, there's no force of tension. You know what, I want to add one more force here. Force of air resistance, F-A-R. Force of air resistance. This is a lot like the force of friction, so it also goes opposite to motion. But it's opposite to motion in the air, so you could have like the air itself is moving, like if it was really windy and it was pushing this book along or something, that's not going to happen. But if the object is moving versus the air, then you might have to deal with air resistance. The question though, you don't want to just say, I mean, I'm going to write it, moving versus air, but we should also recognize that, like, I'm moving through the air right now and I am not concerned with wind resistance, but if I was going like really, really fast, faster than I can run, I don't know, falling out of a plane, then air resistance would be a factor. And so you kind of have to look at both, is this thing moving fast enough for wind resistance to be a factor, and is this object the right shape to be bothered by the wind? Like, if I had a big poofy coat on, I'd be more likely to be bothered by the wind than in the clothes that I'm currently wearing. So wind resistance or air resistance is something we really have to look at a case-by-case basis. Like, do I think this is going to be important here? And I don't think it's going to be important for this book sitting on a table. All right, so this one is done. All right, let's look at a soup can hanging from a string. You can draw anything as just a box. I'm going to give it a little bit more detail. There's my soup can, and it's hanging on a string. I don't even want to draw anything complicated. Soup can on a string. Great.
Telephone?
No, just recording a video, kind of post it up there.
Oh my God.
Now you're on. Hey, come on
You're
in,
in
Miss
the middle.
Ramos. Come on over.
So
Say
sorry.
hello.
So
Say
sorry.
hello.
I actually thought you were just doing a one-on-one.
No, we're always doing one-on-one. And, well, what about all the other kids in the class? You don't see them? You're invisible?
Can I ask you something?
Yes.
I didn't mean to interrupt.
I'll press pause for a second.
Like, I'm so sorry.
Wait,
All right. Hey, the video is continuing.
Do I write next to a book sitting on a table like force of gravity and force of normal force?
So you don't need to write that on there, just this, FG and FN. You don't need to write it out any more than that. You're going to very quickly get to the point where you know what those mean. If we have multiple applied forces acting on the same object, you might want, or you would want to specify in some way, like force applied 1, force applied 2, force applied by Steve, force applied by Mary, just put extra little letters next to it, like build up those subscripts to make it clear what you're talking about, but force of gravity, force normal, and that's fine. In another class, if you're taking this in college or something, you might just use an N for that. For tension, you just might use a T. You might just use a G. But I think that's more confusing to not specify that it is, first and foremost, a force. All right, so we've got this one. This soup can, is it on or near the surface of the earth? Yes. We've got what force?
Gravity.
And which way is it going?
Down.
Force of gravity going down. Next, I would say, is this soup can on a surface? No, so we don't have a normal force, and in addition, we're not going to have a force of friction since it's not moving versus the surface. Is there anything pushing or pulling on this soup can? No, it's not. There is a string, and you might say, oh, something's pulling on it versus the string. If it's going through a string, I'm just going to call it force of tension. So there is a force of tension, and that force of tension is going away from the can in that direction. We're not working on the math part of it now, but we would say this thing's not accelerating, so these two forces, they're the sum of the forces, they must add up to 0. That's the math part of this, where you say this plus this equals 0. You know what the force of gravity is, you can figure out the force of tension is. All right, so these are the first two. Let's go on to that third one. In that third one, we're looking at a garbage can being dragged across a driveway. Suddenly it got complicated. Do we want this driveway? Hey, is your driveway flat, uphill, downhill?
It's flat.
It's flat. We're going to draw it flat then. If we've got a flat driveway and we've got this garbage can here, and we're pulling this garbage can that way, you know what? I'm going to label that. I'm going to put a V here. V. Meaning this thing has a velocity in that direction. All right, well, let's start labeling some forces. I already started putting in an arrow for an applied force. Force applied, because someone's dragging this thing. But is it on Earth?
Yes.
Yeah, so we've got the force of gravity, and that's going down. Is it on a surface?
Yeah.
Yeah, so we've got a normal force coming up and out of this surface. The driveway's flat, so that normal force is straight up. Is this thing moving versus the surface?
Yeah.
Yes, it's moving that way, so we have a force of friction going in the direction that's opposite to motion, which is that way. Force of friction. What next we want to ask? Is anything pushing or pulling? Yeah, we've got that. You could say like, well, this garbage can has something in it that's pushing down on it. I'm treating the garbage can as a whole, including the stuff in it, so we're leaving that out. Is there any ropes? Nope. A rope? Nope. Is this thing moving versus the air?
Yeah.
Yes. So we could say there's a force of air resistance. Any problem that you're doing with this, you would probably ignore air resistance unless you have reason to think that the air resistance is a big force. Like, if you were putting your garbage cans out and there's hurricane winds,
Yeah.
you got to think about wind. If your garbage can is totally empty and it's just a little windy, it's probably going to blow away or fall down or something. But for the most part, you're not thinking about air resistance when you're moving a garbage can. You're not like, oh, I would have been able to move that garbage can were it not for that darn wind resistance. So we're mostly not thinking about air resistance with this kind of one. These are all the forces acting on this object. What's the next one? A ball falling through the air. Well, that was a hard picture. This is an easy picture. Here's a ball. If it's falling through the air, it's mostly going down. Do you want to show it going straight down or kind of sideways?
Straight down.
Straight down. This ball is going straight down. And I drew a downwards arrow and I put a V so it has a downwards going velocity. All right, is this ball on or near the earth?
Yeah.
Yes, what force is acting on it?
Ground.
And which way is that going?
Down.
Force of gravity is going down. Is this ball on a surface? No, so we don't have to worry about the normal force, and we don't have to worry about friction since it's not sliding on the surface. Is anything pushing or pulling on this ball? Nope. Is there a rope on this ball? Nope. Is it moving versus the air? Yes, it's moving versus the air. The ball is moving down, so we have a force of air resistance moving up. And if this ball is moving slow, that air resistance is small. If this ball is moving fast, that air resistance is big. All right, so that is number 4. On to number 5. I'm actually going to do 5 and 6 and 7 all sequentially. I'm going to do the same set of pictures here. When we have a child in a tire swing hanging from a branch, all right, well, here's the tree. We can only see half of it. All right, here is the tire swing. And here is the child. The child is a box, mostly. All right? We are analyzing only the forces that are acting on this box. You're going to see there's 3 really identical looking lines there, but we're analyzing a different thing. The first one we're analyzing the child, and the next one is the tire swing, and the next one the tree branch. When we're analyzing the child, we're only concerned with the forces that are acting on the child. All right, well, the child is on or near the surface of the earth, so they got the force of gravity going down, force of gravity. Then we say, is this child on a surface? And we say, yes. So there's a normal force coming up and out of this tire swing. Now, I just want to pause for a second and say, that force that the tire swing is exerting on the child, the normal force, when we go to analyze the tire swing, we'll also have that force, but it's going to be an applied force because the child is pushing on the tire swing. Those pairs of forces, that's that Newton's third law where every action has an equal and opposite reaction. It's really just this idea that it's a record-keeping thing in my mind. how the force between two objects can be thought of as affecting one or the other, but it really is affecting both, but you're only thinking of one object at a time. So we have this force of gravity and the normal force. All right, well, is this thing on a surface? Yes. Is this child sliding versus that surface? No, so we're not concerned with force of friction. Is the child being pushed or pulled upon? No. Is there a rope here? Yes, but is it attached to the child? No. Is the child moving versus the air? No. These are the only forces. This one is done. You know what? I'm going to erase it and just draw from this same picture. We are now on to number 6, and we are analyzing the tire swing. Is the tire swing on or near the surface of the earth? Yes. So what force do we have?
Gravity.
And which way is that going?
Down.
Force of gravity going down. Is the tire on a surface? No. So we do not have a normal force. Is the tire moving versus the surface? No. So we don't have the force of friction. Is anything pushing or pulling on this?
Yes.
Yes, the child is. So we've got an applied force downwards. Force applied is acting downwards. What next? Force of tension. Any ropes on this tire swing? Yes. And the force of tension is going upwards. The force of tension always goes away from the object in the direction of the rope or string or cord. We're going to see soon that the force of tension, as felt by the tree, is actually going in the opposite direction, even though it's that same force. All right, so we got this. What else? Is this thing moving versus the air? No. So this one's done. Next one. Same picture, but we're looking at the tree branch. All right, so. All right. I'm cutting off the bottom of that tree there so we can see. I'm going to treat the whole tree as one thing, not just the branch. Is this tree on or near the surface of the earth? So what force is acting on it?
Gravity.
And which way is that going?
Down.
Force of gravity is going down. Is this tree on a surface?
Yes.
Yes, it's on a surface. So we have a force coming out of that surface that supports the tree, and that's called the normal force, and it's coming straight up out of the ground. All right, so we've got that. Oh, is this tree moving versus the surface?
No.
No. Would you say, like, would it move were it not for friction? No, we're going to say there's no friction here. This is not like a friction type problem. Arguably, there's some, but it's not what's happening here. Is anything pushing or pulling on this tree?
No.
No, not directly. It's going through that rope. So there's a force of tension, and the force of tension goes away from the tree in the direction of the rope. That is downwards, force of tension. Is this tree moving versus the air? No, it's not. I mean, on a windy day, it's not in this problem. So we don't have to worry about friction or wind resistance. And this one is done. And again, if we were to turn this into a math type problem, we would say this plus this adds up to the acceleration of the tree. What's the acceleration of the tree? Nothing. So this plus this equals 0. It tells you how big those numbers are if you can calculate some of them. All right, so a bucket being pulled up from a well. That sounds like one is moving. A bucket being pulled up from a well. Okay, there's the well. Is anything in this bucket?
There could be.
What do you think? What do you want to put in there?
Water.
Water. Here's the water in the bucket. Okay? That's the water in the bucket. That's going to change things very slightly, but it's just fine. All right. Is this bucket on or near the surface of the earth?
Yes.
So what force is acting on it?
Gravity.
And which way does that go?
Down.
Downwards. Good. Is this bucket on a surface?
No.
No, so there's no normal force. And it's not sliding against a surface, and so we don't have the force of friction. If this had been like a crooked well and it was rubbing against the edge, there'd be friction. There's not here. All right, so there's no normal force. There is no force of friction. Is anything pushing or pulling on this bucket?
Yes.
What is pushing or pulling on this bucket?
The rope is falling on it. And
Okay.
then there's like water and then pushing.
Okay, so we've got those two things. Tell me how to label.
For the pulling, it would be applied force.
So
or
we can say both of these are applied force, but if we're pulling through a rope,
then it's force of tension.
force of tension. So I would call this one force of tension, and I would call this force that the water is applying on the bucket, I would call that one, Nick, hello. I would call that one that's just a force applied. That one is a force applied.
Where did one go?
So different people went to different places. Nick, take out that forces number 2. I'm recording a video of us going through the answers to this one. All right, so that is number 8, a bucket being pulled up from a well, and I think those are all the, oh wait, we didn't look at one of these, which was, is this thing moving versus the air? It is moving versus the air because it's getting pulled up. So it has kind of a velocity that's going up. So there is an air resistance that's going down. I would look at this and I'd say it's probably not a major contributor to this problem because you think a bucket, it's probably not moving very fast in there, and it's probably not the right shape to be really pulling against the air unless this is really tight. But I'll throw it in there. Force of air resistance. But it probably wouldn't, if you were solving a problem like this, they'd probably say ignore air resistance. But it might be there. All right, so that is number 8. All right, and we'll go on to number 9. Number 9, a skydiver falling through the air. Here's your skydiver falling through the air. Are we all right with it being just a box, or should I draw it more to it? All right, that's the skydiver falling through the air. Falling downwards through the air, probably, right? All right, so V, going downwards. Is this skydiver on or near the surface of the Earth?
Yep.
So what force is acting on the skydiver?
Gravity.
And which way is that going?
Going down.
Going down. Force of gravity. Is this skydiver on a surface? No. So we don't have to worry about the normal force, and we don't have to worry about a force of friction that this skydiver is rubbing against things. Is anything pushing or pulling on this skydiver? No. Is the skydiver attached to a rope? No. Is the skydiver moving versus the air?
Yes.
Yes, this is one that we would need to look at. In fact, it'd be a major contributor to what's happening with the skydiver. There's a force of air resistance, and it's going up because the skydiver is going down. So, in fact, when you jump out of a plane, the force of gravity is the same the whole time, the whole way down. But at first, when you jump out of the plane, or let's say you jump out of off of an antenna or a tower or something really high and there's not wind, when you jump out, you're not moving very fast yet. So this force, which depends on how fast you're moving, isn't very big at first. But once you start going faster and faster and faster, this gets bigger and bigger and bigger, and at some point it gets to be exactly the same size as this. And then you stop speeding up. And when you've stopped speeding up, we call that velocity your terminal velocity. It's the final speed that you've reached. It's the highest speed that you reach. And you reach it after something like 100 feet or something. You hit a terminal velocity of something like 100 miles an hour. And you stop going faster, and these two are the same size as each other. All right, so that is number 9. Let's take a look at number 10. Number 10 and 11 are similarly looking, like with 5, 6, and 7. Number 9 and 10 are looking at 2 objects in the same scenario. So number 9, we're looking at a skydiver, but now he's got a parachute. So here's the parachute. There's the parachute, and I'm going to draw all the lines of this parachute going to one central location and then going straight down so that I don't have to look at a bunch of different tensions. But I'm giving away one of the forces that's there. Well, first, let's start with an old classic one. Is this guy on or near the surface of the Earth?
Yeah.
Yes, and the person is the box, okay?
Yeah.
All right, so force of gravity in which direction?
Down.
Good. Is this person on a surface?
No.
So there's no normal force. And they're also not sliding versus a surface, so we don't have to worry about force of friction. Anything pushing or pulling on this person?
Yeah, so force of tension.
Yes, there is an applied force, but it's going through the rope, so we're calling it force of tension, and it's going away from the skydiver in the direction of the rope, which is upwards. Force of tension. Is this person moving versus the air? Yes, so what force do we have?
Force of air resistance.
Force of air resistance, that's right. And we would need to know which way this person is going. Well, the person's going down, and so the air resistance is going up. Now, air resistance does impact the person directly, but it is a major important thing about what's happening when you're using the parachute. But the more important thing is the air resistance on the parachute rather than the air resistance on the person. The air resistance on the person when you're using a parachute is not some huge number. If you fall out of an airplane, you keep falling until your speed hits like 100 miles an hour or something. But when you're falling with a parachute, you're not moving at 100 miles an hour. You're moving at a much lower velocity, which is survivable when you hit the ground. If you had no parachute, you would also be going at a terminal velocity. If you have a parachute, you're also going to be terminal velocity, but your terminal velocity is in lower numbers, right? That's it. All right, so these are the forces that are acting on this scenario. Let's look at this same scenario, but now with regards to the parachute. So rather than looking at the person, or did I say skydiver, we are looking at the parachute itself. Is this parachute on or near the surface of the earth?
Yeah.
So what force is acting on it?
Gravity.
And which way does that go? Force of gravity. And is this parachute on a surface? So there's no normal force. And there's not on a surface, so there's no friction. There's just air resistance that is going down. Air resistance that is going up because the object is going down. Force of air resistance, and there's a force of tension going down through that rope. Force of tension. And those are the only forces acting on the skydiver. The parachute, I mean. Last one, a rocket going up. Here's a rocket, and it's moving upwards. So we've got a velocity vector going upwards. It said it's going upwards through the air, so this thing is still near enough to Earth that we've got a force of gravity, but it's not on a surface. There's no friction. There is air resistance, so we've got a force of air resistance going down, and there must be some force that's applied that's making it go up, and that's actually called thrust, but we're just going to leave it as a force applied. And that is the end of this one.
I have the graphing number 1, but I literally only have 2 questions done. There's still kind of there.
Yes. What's going on with this thing? I gotta stop the video.